All right, so yesterday, what was the last thing that we were discussing on this? What happened to force when we changed the radius, right? That's what we were working on? All right, so let's work on that more, because that's the thing that messes everybody up. So here again, we just have two objects, right? They both have their own mass. So we're going to label mass 1 and mass 2. We could label it mass Fred and mass Bob. It doesn't matter. Any two masses, right? The distance between them, we're just going to call it radius. You could call it a d for distance. It doesn't matter. Yes. This is what we went over yesterday. Yesterday I told you that the force of gravity between the two objects was related by taking the universal gravitational constant, big G. This is already in your notes, unless you didn't write it down. Times mass of the first object times the mass of the second object divided by the radius, the distance between the two objects squared. And we were talking about how attractive am I, right? And we said that for me to increase my attractiveness, I had two possibilities, right? I could go out and eat a bunch of donuts and gain a whole lot of mass. And if I had a big mass, then I would be very attractive. Okay? Because the force of gravity is based on that mass. Right? What was the other way that I could increase my attractiveness? How can you increase the force of gravity between two objects? You can bring them closer together, right? The closer two objects are, the more they pull on each other. Right? So if you want to increase the force, just bring the two objects closer together. Now, yesterday we were relating the force of gravity to the distance. And we said that the force of gravity was proportionate to that distance squared. It was inversely proportionate, which means you do essentially the opposite. So if you bring the objects closer together, if you make r smaller, then F does the opposite and it gets bigger. Right? But it's not opposite, because if I make r twice as small, I don't make force twice as big. That would be inversely proportionate. But this is inversely proportionate to the square. And so we said yesterday that if I made the force twice as big, so I made a 2r there, then I'm adding a 2 to the r. But the r gets squared, so this 2 is squared, and so it's like adding a 4 on this side. So if I add a 4 on the bottom side on this side, then I got to add a 4 on the bottom on that side. So if I make the distance twice as big, 2r, then I make the force 4 times smaller. And that's kind of hard for students to get. Okay?
That's for moving apart, right?
That's if you're moving the objects further apart. If you double that distance, then you make the force 4 times smaller. Yes, sir?
So you wouldn't have to, on the first one, you wouldn't have to put it divided by 2?
No. No.
It's just a 4 for the
On the first one, if you put a 1 here, 1 squared is 1.
Oh, okay.
Right? And so then you put a force over 1, but that's still force. So you don't have to do it. But if you put a 2 there, if you double the distance, then it's a 4. If you triple the distance, what did we say that was yesterday? It would be 9 times more. Because we're going to square that 3. And so it's like putting a 9 on that side. That part, usually after I point it out and show a couple of examples, students normally don't have a problem with that. And it makes sense. The further apart I get, the less the force is. All right? The part that messes students up is how do you mathematically calculate if you bring the things closer together? We know what happens to force when you bring the objects closer together. Does it increase or decrease? It increases, right? If I bring the objects closer together, it increases the force. So what I want to do is I want to say, well, how does that work? Mathematically, how do I know what's going to happen? And so I go back to my exact same situation where I have force related to the inverse square of the distance. Now, instead of multiplying by r, right, I'm going to cut the distance in half. So I'm going to have 1/2 R. So now I have force is proportionate to 1/2 R. But remember that 1/2 R is squared. Right? So if you take 1/2 and you square it, what do you get? 0.25, or what's the fractional equivalent of 0.25? It's 1/4. Okay? It's 1/4. Now, yesterday at the end, I said kind of, as like a little side comment, like hopefully you learned this in math class. That's what I said. The problem with that assumption is that I know that a large percentage of you did not learn that. Whether you were shown it or not, for some reason, that doesn't stick with my students. So I'm going to go through how to square a fraction just to make sure everybody's okay with this, and then we'll go on, I promise. All right, so if we have 1/2 squared, that's the same thing as saying 1/2 times 1/2, right? 1/2 times 1/2 is 1/2 squared. How do you multiply fractions?
Bottom times bottom is across it.
You just multiply across, right? So we take the numerator, we multiply it times the numerator, so we multiply it across the top. So 1 times 1 is equal to 1. Then we multiply across the bottom, the denominator. So 2 times 2 is 4. And so that's why when you square 1/2, you get 1/4. Okay? If I were to square 1/4, then that'd be 1/4 times 1/4. So now I end up with 1 times 1 is 1. 4 times 4 is 16. Right? Now you could say it's the same thing as saying 1 squared over 4 squared. And 1 squared is still 1. Sorry, you can see that. And 4 squared is 16. That still works, but sometimes students have a hard time with that little leap. Okay? So, but this is really what you're doing. 1/4 times 1/4. You multiply across the top, you multiply across the bottom, and then you end up with what you want. All right? What if you take 2/3 and you square that? Then what do you get?
4/9.
Then you get 4/9. Right? Because it's like 2 times 2 over 3 times 3. 2 times 2 is 4. 3 times 3 is 9. I get 4/9. And 4/9 does not simplify. And so I just leave it 4/9. Okay? So that's the mathematical skill of squaring a fraction. So now we're going to take this skill and we're going to apply it to our physics. Because remember, physics really isn't just math. There's other stuff to it. It doesn't seem like it, but at least in the beginning part, it seems like all math. All right, so if I take my force and I relate it to the distance squared, but now what I'm going to do is I'm going to take my distance, and instead of making half the distance, instead of making 1/4 the distance, what I want 1/3 the distance. Okay? So I'm going to cut the distance by 3. So I'm going to have 1/3 the distance. What's going to be my force?
It's going to be force.
What's the force going to be?
1/9.
Well, 1/3 squared is 1/9, right? So I have force is proportionate to 1/9 r squared. Right? But if I have 1/9 on this side, then I got to divide by 1/9 on the other side. Right? But that really doesn't tell me what happens to the force. Right? You're right. It is the force divided by 1/9. But what does that really mean? Well, what that really means logically, so that people can actually make sense of what's going on, what do we know has to happen to force if the objects get closer together? If the objects get closer together, do you have less force or more force? You have more force, right? As they get further apart, things get less attractive. That's why long-distance relationships don't work out, right? As you get closer and closer, then they, actually, well, never mind. But as you get closer and closer, you get more attractive, right? The force increases, right? So if the force increases, then what you really need to do is you need to look at this and say, okay, well, what's really going on? Well, remember from math class, if you divide by a fraction, that's the same thing as multiplying times the inverse of the fraction. What's the inverse of 1/9? That's 9. Okay? So I could also say, this is true, by the way, but I could also say that instead of dividing by 1/9, what I'm going to do is I'm going to multiply times 9. So when I make the distance, okay, 1/3, so I have 1/3 the distance, then I've increased the force of gravity 9 times. That's the part that students have a hard time with. Most students don't have any problem whatsoever once I do a couple of examples of if I increase the distance, what happens to force. That part's no problem. It's this other part that messes people up. So we're going to do another example. Okay, so we have force is proportionate to 1 over r squared. So if I make this, I don't know, somebody give me a number between 1 and 10. 5? Okay, so we're going to make 1/5 the distance. Okay, so now it's going to be force is proportionate to 1/5 r squared. What happens to force? What is force proportionate to? What happens to the force? Does the force get smaller? If the objects get closer together, if now we went from r to 1/5 r, what happens to force?
It's getting bigger.
It's got to get bigger, remember? When objects get closer together, they're more gravitationally attractive. Okay? So, when objects get closer together, they're more attractive. So we know force has got to go up. But by how much does the force go up? What's 1/5 squared? 1 over 5 times 1 over 5. What's that come out to be? 1/25. Right? 1 over 25. What's the inverse of 1 over 25? 25 times. So the force increases by 1 over 25. So by making the force, by making the distance 1/5 the original distance, I have to square 1/5, so I get 1 over 25. And then when you divide by 1 over 25, that's the same thing as multiplying times 25. Questions on that? So I'm going to have you do an example, and I'm going to walk around the room, because I know there are more questions than y'all are asking. Yes, sir.
How is
Good.
How is it times 25 instead of dividing it down?
Okay. So the question was, how is that times 25 instead of dividing? Well, remember here, we said it's having 1/5 squared is the same thing as 1 over 25. Well, we learned from math class, your algebra class, that anything you do to one side of the equation, you got to do to the other side of the equation. So here I have 1 over 25 on this side of the equation. So I have to put 1 over 25 on the other side of the equation. Right? That's what I have to do from algebra class. But force divided by 1 over 25, that's very hard for people to logically reason through what is actually happening to the force. So what I have to do is I have to say, well, 1 over 25, that's really, if I divide by 1 over 25, that's the same thing as multiplying times the inverse. So now I get 25 times F is proportionate to 1/25 r squared. So we started out with something that seemed fairly reasonable. If we double the distance, then we decrease the force by a factor of 4. But when we go the other direction, then it gets a little bit sticky. So now what I want you to do as an example is now I'm going to take my original distance, my two objects, with a radius of r and a mass of m1 and a mass of m2. And now what I'm going to do is I'm going to decrease r. So I'm going to make r smaller. And r is going to be smaller by a factor of, I don't know. We already did all those. So why don't we do, y'all know what 6 squared is?
Yeah.
All right. So by 1/6. We're going to have 1/6 r. So I want to know what happens to force. What happens to force when we make the distance 1/6 r? What happens to the force? Y'all work on this. Does the force get bigger or smaller, and by how much?
It gets bigger, right? What's 30 times bigger?
You got 6. We don't have to do this on Tanner. Oh, you made it 1/6. Yeah.
6,
So I had to take a 6 and I got to square that. 6 times 6 is 36. Since they got close together, they got big. That means you got 36 times 50. If it made it 6 times further away, then it'd be 36 times smaller. What do y'all do? You got 36? And 36, fantastic. How was it great? Okay? 36? 36, that makes sense. Yeah. So you're almost there. So if you divide by 136, that's the same thing as multiplying times 2. Yeah, but do you understand what you're doing?
Yeah, it's
Because you're never quite there. So, okay, well that's fine, but that's something, right? So now you know it changes by 36, right? So is it getting bigger or smaller? The force, yeah, it's getting bigger, right? We got close to so it got bigger by 36. Because I tell you, if the distance is 1/6 r, that means it's got smaller. Does this make sense?
Oh, he knows. He
Get it right started. Okay. Does this make sense? That part comes in right here. Okay, so it looks like the vast majority of y'all you either got the answer or you got very close. All right? So we come back over here and we say, if we have 1/6 R, that's the same thing as saying force is divided by 1/36. Right? And so, because that's 1/36 R squared. So if that's true, then force divided by 1/36 is the same thing as force times the inverse of 1/36. So, because dividing by a fraction is the same thing as multiplying times the inverse. And so then I have 36F is proportionate to 1/136 R squared. So if I make the distance 1/6 what it was originally, I got to square that. That's where I get the 136 from. And then when you divide by 136, it's the same thing as multiplying times 36. All right. Now, one more little piece, and then I will let you work. It's the way. It always takes longer than I think it's going to take.
It's fine.
Yeah,
But that's good.
It's good. To learn.
All right. So one more piece. This is the easy part. Easy-ish part. All right. Remember, we had force is equal to big G times the mass of the first object times the mass of the second object divided by the radius squared. All right? Now, we just did what happens if we play around with R. So now we're going to ignore R for a minute, and we're going to talk about mass. We have qualitatively, meaning kind of what happens without any numbers, talked about if I wanted to increase my attractiveness, I would just eat a bunch of donuts and I would increase my mass. And that would make me more attractive. Okay? So mathematically, let's look at that real quickly. If force is proportionate to mass, because remember, if F is on the top and the M is on the top, that means the two are proportionate to each other. Okay? That was from math class. Right? If I double the M, so if I get twice as massive, if I double how much mass I have, what happens to force? It gets twice as big, because anything I do to this side, I got to do to that side. So if I go out and eat a bunch of donuts and gain twice my weight, then I'm going to be twice as massive. So I'm also going to be twice as attractive. Okay, gravitationally speaking. All right? Now, I could also do the same thing. What if I increase my mass by 4 times? Then how much would the force increase by? 4 times, right? This gets boring really quickly. All right? Now, but notice, force is proportionate to both mass of one object and the mass of the other object. So this could be slightly more fun, right? Because we've been talking about what happens if Mr. Martin eats a bunch of donuts, right? And then Mr. Martin gets more mass, right? And I increase my attractiveness. But what if the Earth eats a bunch of donuts? And the Earth gains a bunch of mass by eating a lot of donuts. Not that it can do that, but if it did. What if the Earth gained a bunch of mass? Then what would happen? The gravitational force would increase. And in fact, the planet in the solar system that is, well, like that, right? And then this would be the big planet. It doesn't even fit on the page anymore. That would be Jupiter. Jupiter ate lots and lots of donuts. Okay? Jupiter has 3 times the force that the Earth has, based on where you're standing at on its surface. Right? It's way more massive than the Earth, but Jupiter is the example of if you increase the mass of the planet, what happens to the force of gravity? It also increases. So what if I eat a bunch of donuts and the Earth eats a bunch of donuts? Then what happens? Well, then my attractiveness increases, the Earth's attractiveness increases, and we have to combine the effect. Right? So let's talk about that for a second. So we have the force of attractiveness between the Earth and the 2 masses. Right? They're directly proportionate. So if I double my mass by eating a bunch of donuts, what happened? If I just double my mass, I left the Earth alone for a minute. If I just doubled my mass, what happens to force? It doubles, right? It got twice as big. Anything I do to one side, I got to do to the other side. Now, what if the Earth then all of a sudden eats a bunch of donuts, and the Earth gets twice as massive as well? Then what happens? Well, then I added another 2 on this side, right? And the Earth got more attractive, not less attractive, because I like donuts, right? So I like Earths that eat lots of donuts. And so therefore, I had to add another 2 on this side. If I double my mass, then I double the force. If I double the Earth's mass as well, then I double the force again. So that's the same thing as saying that the force increased by 4 times because I doubled the mass of both of those 2 objects. The effect is also increased. By increasing the mass of one object, then you just increase the force by that amount. But if you increase the mass of both objects, you have to include both objects' increase. So it totals. So let's look at that